On this video, we're going to look at state change and the kinetic molecular theory. We have 6 different state changes. We have freezing, going from liquid to solid, melting, going from solid to liquid, sublimation, going from solid to gas. Sublimation is very rare, but it does occur. Evaporation, going from liquid to gas, condensation, going from gas to liquid, and deposition, going from gas to solid. Deposition is also very rare, but it does occur. Then below, I have a diagram for you that will help you remember these different state changes. We have an example of heating and cooling water. So when we have an ice and we melt it at a temperature of 0 degrees Celsius and pressure of 101.3 kilopascals, it's gonna go from ice to liquid water, and then we boil the water at a temperature of 100 degrees Celsius and pressure of 101.3 kilopascals to water vapor, which is a gas. And then we cool the water vapor at a temperature of 100 degrees Celsius, that is condensation. So we cool it to liquid water, and we freeze the liquid water at a temperature of 0 degrees Celsius and pressure of 101.3 kilopascal. We freeze it to ice. It is possible for water to boil at a much lower temperature if the pressure is reduced to plus or minus 3 kilopascal. So I told you that pressure plays a very important role in state changes. So we can see here that if you reduce pressure, then you are going to boil your water at a much lower temperature. So that is how pressure affects state changes. We have an experiment here of state changes. We're going to look at heating curves and cooling curves. So how do you do a heating curve or a cooling curve? Method of determining a heating curve. So you set up a tripod stand with a gauze over a Bunsen burner. I don't know if you do know these apparatus, but you don't really need to know them. You fill a heat-resistant glass beaker with plus or minus 100 milliliters of water and add a few blocks of ice. Remember, this is a heating curve, so we're going to be heating ice. You stir the contents well and take the temperature reading on a thermometer. Ignite the Bunsen burner and start the stopwatch at the same time and take a temperature reading every 30 seconds while stirring continually. Then you tabulate your data and draw an appropriate graph. On this slide, we have our data. So time was recorded in intervals of 30 seconds, and temperature was also measured using a thermometer. And then we have our heating curve. So from A to B, we still have ice, because remember we said that water melts at 0 degrees Celsius. So below that, we still have ice. At 0 degrees Celsius, it starts to melt. So from B to C, as you can see, temperature doesn't change. What does this mean? This means that we have a state change. This is where melting occurs from B to C. This is where ice is now changing to water. So it's going to take time. That is why temperature stays constant from B to C. Then from C to D, now our ice has melted and we have liquid water. From C to D, we just have water. Then from D to E, we have another state change. Now we're going from liquid water to water vapor. So from D to E, it's another state change. That is why you can see from 210 seconds to 270 seconds, the temperature stays at 100 degrees Celsius, because that is where water boils, at 100 degrees Celsius. So that is where we get the boiling of water. Then from E to F, we have our vapor. That is our heating curve. Our cooling curve, the figure 3.3 on the left, shows a cooling curve. So it's an opposite of the heating curve. So we also have state changes where water vapor changes to liquid water, and also where liquid water changes to ice, to solid water. So you should just know that whenever you see a constant temperature, you need to know that you have a state change where the temperature is constant. Okay, the kinetic molecular theory. We'll look at solids, liquids, and gases according to the kinetic molecular theory. The kinetic molecular theory gives a description of matter at a microscopic level. It describes that all matter is composed of small moving particles. It is used to explain the different states as well as the transition between the states. It also explains the observation at a macroscopic level. Let's look at the particles in solids, liquids, and gases. How is the distance between particles? In solids, the particles are closely packed in an orderly arrangement or crystal lattice, and solids have a high density. I hope you still remember density from the properties of materials that we did in chapter 1. And then liquids have particles that are close together and they have no regular arrangements. Liquids are less denser than solids. And then gases, they have particles that are far from each other. They have irregular arrangement and very low densities compared to solids and liquids. How is the motion or movement and the kinetic energy? So in solids, the particles vibrate only in their fixed positions because obviously the particles are closely packed, so the only movement they can make is just vibration, and they have a very little kinetic energy. In liquids, the particles move freely across each other and take on the shape of the container. If you still remember when I introduced the states of matter, I did say that liquids take on the shape of the container and they have more kinetic energy compared to solids. Gases have particles moving around freely and they fill the whole space in which they occur, and gases have a much higher kinetic energy compared to both solids and liquids. How are the forces between particles? Solids have strong forces of attraction and repulsion between particles, which explains why their particles are closely packed. Liquids have weaker forces of attraction and repulsion than in solids, and gases have very weak forces, and repulsive force increases when a gas is compressed. So when you compress a gas, you increase its pressure and reduce its volume. How is compressibility? Solids are not compressible, liquids are not compressible, but gases are compressible. Pressure, so solids exerts a downward force on the surface on which it rests. So the pressure exerts a downward force on the surface on which it rests, on which the solid rests. In liquids, pressure is exerted in all directions on the walls of the container. In gases, collisions between particles and with the walls of the container cause internal pressure. So we get internal pressure in gases. That is why it is much more easier to change volume and pressure in gases, and it is not so easy to change volume and pressure in solids and liquids. That is it on this video. On the next video, we're going to explain temperature increase and decrease and state change in terms of the kinetic molecular theory.